Welcome to everybody. What do you see here is the 7th lesson of the drive technique, 7th lecture of the drive technique topic. And last week we were talking about batteries, battery types, and battery characteristics. And this week we continue from here. And the next topic actually is the charging of batteries, really in a nutshell, just for having an idea about the more often used types of battery. So charging of batteries. Charging of batteries. Let's start with the traditional, what we call lead acid battery. PB battery. There's a whole science and a lot of experiments for charging the lead acid batteries. And we may say we get the following characteristics when charging. Here we get the time, roughly, and here we get the other values. And the other values are changing by the following way. Let's have first a current that starts at a constant value, then decreases, then remains a small constant value. And using that, we can define, more or less precisely, we can define 3 zones. So here, this is the current I, and the starting current, this value is roughly 10% of the I maximum current that can charge the battery. And here the last value, if I try to symbolize it, it's less than 1% I max. Okay? So we start with a quite high current when we charge, and then the current goes down along a ramp and remains at a small value. How the tension changes in this case? The tension of the battery changes by the following way. We get a quite small value that goes up to a given value. It becomes stabilized and get a more or less constant shape that we call U max, maximum tension. In case of 12 volts, let's say we get 14.4 volt. And then we leave it as such, and there's a jump after the switch off of the large current, and we get a U nominal that's around 13.4 volts, let's say. Okay? So we get 3 quite different stages if we consider the current and the tension. Stage 1, stage 2, and stage 3. And what are the characteristics of these stages? The names for the zone 1, it's the full charging. When we charge up the battery up to its capacity. The strong current till the tension of the lead battery reaches the nominal or the maximal value. What happens once we have reached the maximal value? If we continue the high current, it will start to boil the water in the electrolyte. So it's not needed to continue. And the bubbles in the electrolyte can remove the the jelly material from the lead grid. So it's dangerous. So we've got to shut down the current. And the phase 2 is what we call, what is the English name for that? Let's say it's soft charging. When we follow up the charge supporting capacity of the battery, and when we cannot add any charge at even a small current, then we switch to the mode 3, and the mode 3 is the drop charging. When we add very little current, and this very little current is added to keep the battery's charge at the top. You know that every battery has got some internal resistance, as every electric device. And the drop charging adds just the current required to win the internal resistance. So it's a very small value. And this is the typical case, for example, for motorbikes that are stored for the winter. You add a drop charger to the battery, and on the spring you can start to use your battery as usual. It will not drop the charge, and it will not drop the capacity, and the battery is kept alive by drop charging. Okay, so here current for the consumption of the internal resistance. Internal resistance of the battery. So, and what about the charge? The state of charge here, SOC, is 80% roughly here at the limit of the first zone, and state of charge is like roughly 90, not 99, let's say 98%. Okay, like this. State of charge being the capacity divided by the maximum possible capacity of the battery. Okay? So, you see, such is the ideal curve. So we've got to measure both the tension and the current that goes into the battery. So we need a control in the charging circuit. We cannot have a brute force full power charging because it will kill the battery. And doing that, so control is required in the charging circuit or in the charging device. And further conditions we were talking about last week. That's the temperature. We've got to check both the temperature of the battery and the external temperature of the place where we are charging the battery. Usually we say if temperature battery is higher than 55 degrees Celsius, then no charging. So this is the overall temperature. Because of the internal resistance, the battery cells are heating up during charging, and if they are too hot, then we stop the charging and wait till they cool down. And if temperature outside is smaller than minus 20 degrees Celsius, or temperature outside the battery is higher than 45 degrees Celsius, again, no charging. If the temperature is too low around, there's just, so the fluid electrolyte cannot move enough. And there is risk of brittling away of the lead pasta from the grid. So it's not good. And if the temperature outside is too hot, the battery will reach quite quickly the 55 degrees Celsius under the charging current. So again, no need for charging. So if you are working in the desert, you need a climatized room for charging the batteries. It seems to be stupid, but it's the case. And if you are working in the north, in Siberia, in Russia, or in Canada, and it's cold outside, you've got to take off the battery from the vehicle and put in a hotter, slightly hotter room to charge again. Maybe I haven't told you that the flat-out battery can freeze. If there's no charge enough inside the electrolyte, it will freeze quite easily and well above minus 20. So if it's really flat out, it can freeze at minus 10, minus 15 degrees Celsius. And once it's frozen, again, you've got to wait till the electrolyte melts, so above 10 degrees, above 0 degrees Celsius, and then you can charge just after. So it's a quite sensitive thing, the charge of the lead batteries. And if you see charging devices, you can say in supermarkets or anywhere else, for sure you get a integrated circuit, a control circuit inside the chargers, okay? I don't know which kind of battery are used in tanks or in military vehicles, maybe lead acid batteries as they are cheap. So you've got to take care of these things. Okay. What is the case for the other type of batteries? It's a quite tricky thing because it depends any time on the battery, what's inside, what are the materials inside, and you've got to get an appropriate charging circuit and charging logic, depending on the battery. So if you had mobile phones, let's say 20 years ago, when we were using nickel-metal hybrid batteries or nickel-cadmium batteries in mobile phones, we had always warnings with the new phone that first charge it completely, then leave it for discharge, and charge only when it's discharged. So these are the properties of the following batteries. For the nickel-cadmium and nickel-metal hydride, M is being the metal globally in chemistry. Nickel-metal hydride battery. They need a forming charge required. Forming charge required before entering in use. And that's because these batteries have got memory effect, so they remember when they was and how they were used, and at which point of capacity, at which point of state of charge they were started to charge or discharge. And this charge also is requiring for decreasing the grain size in the electrolyte, because they have no fluid electrolyte, they have more or less a jelly-looking or solid electrolyte, as I told you last week. So a forming charge is required before entering in use, and the goal is to goal is to erase effects of manufacturing and long storage. Long storage. And what we do with the forming charge is the activation and initial motion of the crystallized electrolyte. Here were these were the batteries when the electrolyte was maybe fluid when charged and crystal when discharged. So if we have to charge it for the first, the electrolyte will change from crystallized state to fluid state. And if there are larger grains in the crystal, we've got to charge, discharge sometimes to make a completely even distribution of the electrolyte. Okay? And having this, some charge, discharge cycles are needed to reach the nominal capacity. So it's just like the breaking in of the vehicles, of the engines. We have to take care of the first charges and discharges. And then once it's in use and the normal conditions of use are applied to the device, then it can give its full capacity. Okay, these are sensitive batteries, but they were much better than the lead acid batteries. And that was the technology level of the, let's say, of the year of the 2000, 2005 years. So 15 years ago, let's say, more or less. I remember my first mobile phone, it has a warning that first charge it fully, then let it discharge, and then charge it again fully, and then so on. Okay? Good. And one more thing. Charging the fully charged battery is harmful. So it makes bad to the capacity of the battery. While a lead acid battery you can charge till infinite without problem with a drop charging to supply the consumption of the internal resistance, in the nickel cadmium or nickel metal hydride case, it's forbidden. Once you have charged it, you switch off and you get a discharge, and once it's flat, almost flat, and discharged, again you plug it in the circuit. Okay, so if you get an older device, I don't know if you're collecting old mobile phones or you are collecting older devices, electrical devices, or you get in the military industry and you get older technology, always check what kind of battery you've got in your device and use appropriate chargers. It's possible that you've got to use a separate charger for your lead batteries, and you have got a separate you have to have a separate charger for your nickel metal hydride batteries. And when your chief is asking why do you need two kind of chargers, a small one and a big one, you may tell because I get different batteries. If you don't want to change often the expensive batteries, small batteries, then it's cheaper to have the appropriate charger. Okay? Good. And then comes the third type of battery that we use quite often these days. The batteries containing lithium. Either lithium-ion batteries or lithium polymer batteries. All these, again, behaves differently. So forming is not required. Initial forming charge. Is not required. And also it's sensitive to flattening out and to overcharge. So here again, no drop charge. If the battery is fully charged, then you've got to cut off the charge. So drop charging is forbidden. And if you want to have a diagram for the charging current and tension, you may say you've got the time, and again, current, constant value, then a ramp to 0. So you get two zones, zone 1 and zone 2. And if you check the charge, or sorry, the tension, this was the current I. And for the tension, you get increase ramp, and this was the tension U here. And for the state of charge, here you get 7 to 80%, depending on the battery state of charge. And here you get 100% state of charge. Okay. And for the phases here, the phase 1 is called the full charging. And the phase 2 is called, let's say, the soft charging. Okay. And there's an example to understand this. And the example is the following. You imagine a movie hall where you get a lot of empty seats. And the first stage is the case when the public enters in the movie hall, and there's a lot of free place, so anybody can sit whenever he wants. And at the end, you've got only a few empty seats left. So for those who arrive late or at the end of the entry period, they've got to seek for the free places. And it's a much slower process than for the first entering people. Okay, this is how you can imagine the first and the second stage. This is usually how the electric vehicles are charged. You've got the fast charging here with high current, not really high current, around 100 volts of continuous current. And once it's done, then you get the remaining time as very small current. Let's say from 100 or 150 amperes, it goes down to 10 amperes. Very smooth for a much longer period. Okay? And note, remark, that for a lithium battery, the tension when flat is around 3 volts or 3.1 volts. And the tension when it's full, it's around 4.05 volts. So you see there's very little difference between the flat tension and the full tension. So you can say that tension level is not giving information on the state of charge. So how we can decide if it's half empty or 25% is left or 75% is left in the battery? We get a very narrow tension interval to see, and usually we cannot decide. So how we can measure the state of charge of lithium-ion batteries? So for lead acid, you just plug in your voltmeter and you see the tension, and you see that it's below somewhere 10 and 14 volts. Here you won't see it at all by just a voltmeter. What you do instead to measure capacity, you need a charge, discharge, charge, cycle, a charge, discharge, charge cycle has to be measured or followed by measuring devices. So, what is the practical side of that? If you get an electric car that uses lithium batteries, let's say the most are using lithium batteries, every year you've got to take it to the service, and the people there usually will check what happens with the charging and discharging. And as for a simple battery, or a simple electric car, the normal charging lasts 4 to 5 hours. The discharge also needs a given time. And the further charge also needs 4 to 5 hours. It takes at least a day to check the battery, a simple battery check. And the mechanic guy is doing nothing, just looking at his watch and checking the ampere and tension levels. Meanwhile, he's doing his other job, so but you've got to leave the car there. I don't know how it happens with the Tesla, but I'm afraid there's also some method like this for estimating. And also, once the capacity is measured for the battery, then usually the autonomy of the car is fine-tuned, so it's set upon what is in reality with the battery. At the Teslas, they are making that software by software, and in the Japanese cars, in Mitsubishi IMEV or the older Japanese electric cars, Mitsubishi IMEV or Citroën C0 Peugeot Ion, it's done like that. Once a year, you go to your workshop, to your dealer, you leave the car there for a day, so you give it take the car a morning, and you get it on the next morning or the next afternoon, and then you get a complete check and control of the battery. So it's not the working that lasts long, but the charge and discharge. And how they can discharge a battery, you got large batteries, let's say half ton of weight. The discharge is as simple as possible. For example, you get the internal heating of the car, and you set the internal heating to the maximum. So you are the heating ventilator going at full charge, and you are waiting some hours. So it's easy like that. Unfortunately, it takes time. I have no information about how Tesla is making that, but I'm sure they got something similar. But as they are more developed on software side, maybe they are just checking charging by charging the things. You can do that only if you flatten out the battery below 50% till 40 to 30%. Then you charge it fully up to 100. Usually, Tesla users can set the properties of the car so not to charge the car over 80% to keep the battery in life for a long time. So, but for this measurement, a full charge is required. So maybe they are also doing it like that. Okay. So if you buy or you intend to buy a second-hand used electric car, it's good to go to a dealer and spend some money and wait a day for making this charging cycle to have information about the state of the battery. And knowing that every battery loses its capacity at a rate of 5% a year, you won't be surprised if they say the battery is perfect, but the range of the car is much less than a new one that it was 10 years ago. Okay? So there's no contradiction between the two datas. Range when new 130 kilometers, range at the age of 10 years, 100 or 90 kilometers maybe. But the battery is perfect. It is, but its capacity is going down and down with the time. Okay? But in the city, in the big city, usually you don't go farther than 30 to 40 kilometers by day. So it's still okay for you, for your everyday traffic and business. Okay? Good. So if you get electric car, for sure you've got to go to the workshops some days, to go to the dealer and check your battery at least once a year. It's not compulsory, but it's better if you do it. Okay. So I want to finish, I will finish this short part for the charging of batteries. So I try to give the basic information. So charging, first check your battery type, then check your charger. If the charger can do the type of charge required for the battery type, and if both are okay, then you can plug in and charge your battery. If you get a charger for lead-acid battery, don't want to charge your lithium cars, it won't go. Okay? Good. And now some words about capacitors. Capacitors, you have learned maybe in physics at the high school. They make energy storage energy storage in form of static electricity. So you got two metallic plates at a given distance. There's some material that separates them, and this material is isolating. It can be the air, it can be a kind of plastic, wood, and so on and so on, but the meaning is that it's an isolating material. And between two plates, you can measure an electric tension if you charge it. And this electric tension is kept there for a given time. We like capacitors a lot because it can be charged quickly, really quickly, in a short time. You can apply high current for short time, bang, and it's charged. And also, it can be, how to say it in English, flattened out maybe, discharged, that's it, discharged. Discharged quickly. So for a battery, if you discharge it with higher current than 10% of the capacity, it can be harmful for the battery. For a capacitor, you get no such problem. You charge it with large current quickly, and you discharge it with large current quickly, and it does not affect the capacity of the contents of the capacitor. So you can be happy because you get no capacity decrease with time. I mean here that if you charge and discharge, the capacity is not depending on the number of charges discharges. Why for a battery it does, for lithium-ion it does. And what is not so good, that it has a self-discharge time. That changes depending on capacitor type. It can be really short, or it can be a bit higher, or smaller. The short, small capacitors, small capacitor that you use in an electric circuit for backup or for for constant alimentation of electrical circuits. You've got in the order of weeks, 1 week or less. It depends how big is the capacitor. If you get a larger size, sorry. The small capacitor in electronics, let's say 1 week. If you get larger capacitors, I've got to erase. Here I say power capacitor. it can keep the charge for a week, again weeks, 7, 8, 10 days. And hybrid vehicle capacitor you've got self-discharge time of months in the months magnitude. Okay. There's no chemical reaction inside. It's just the variation of the electrically insulating material that causes the discharge, plus the resistance of the wires, if any. And note that the capacitor can be paired easily with lithium-ion batteries. With lithium batteries, because it can absorb the overcharging, or in the case of flattening out, it discharges quicker than the flat out battery, so it can protect the lithium battery. Okay. Protection against overcharge and full discharge. So if you get a pair of energy storage devices, both capacitors and batteries, as a couple, they can work quite good together. Disadvantage is that it's more expensive and more complex to use both capacitors and batteries than to use just one type of energy storage device, either battery or capacitor. Okay? And some words about application of capacitors. In vehicles. The simplest application is storage of energy regenerated from braking. When you hit the brake pedal, the car puts a lot of current to the alternator, so you will get a huge quantity of electricity produced. That's put just in a capacitor. The size is like the Boeing. It's large thing. You can find these capacitors in PSA vehicles. PSA is Peugeot, Citroën, now Opel also, and with Stellantis, they are just united with Fiat and Chrysler. But the technology is present mostly in Peugeot and Citroën. But also you find this in Mazda, Matsuda in Japanese, and also Toyota. So quick charging, quick braking, but intensive braking. You charge up your capacitor, and then quick starting, like in cities, if you're hurrying, you discharge your capacitor. That helps the starting of the internal combustion engine, for example, or adds some power for the acceleration. Okay? So mostly in hybrid vehicles. I mean hybrid, these are the so-called mild hybrids. So they get a low tension hybrid subsystem, and the car is driven mostly by the internal combustion engine. Typically, this is like the new Suzuki Swift, where the engine does not stop. It's always working, stops just at red traffic lights, but it's always driving the car. But for braking and accelerating, you get a large capacitor that helps. It stores energy at braking and puts back when accelerating. Okay? For other kind of vehicles, it can be a supplementary capacity for starting the vehicle. I say diesel locomotives. When you get a 16-cylinder large diesel engine in a locomotive, and you've got to start it, either you use large batteries for start, or you use a separate small internal combustion engine for start, or you use a large number of capacitors. For 1 day, 2 days, they can store the energy without problem, and they allow an easy start for the diesel locomotive. And also it's the case of, how to say it in English, if you get vehicles that requires how to say it, a grid of cables like tramway or trolleybus, and there are some zones that for any reason, for example for the city layout or any reason, that's forbidden to have the cables on the air, but the trolleys have to move or the tramway has to move. They can have an auxiliary batteries made of capacitors. Okay, so auxiliary drive. Energy source. And you can have here tramways, and trolleybuses. For example, here in Budapest, you get the red Solaris trolleybuses, the new one. They have got batteries for going till the network and back to the garage. Or sensors in the city center when there are no cables fixed to the houses, then they go by their own batteries or capacitors. Okay. There are also ships using batteries. For capacitors for short distance, and temporary and periodic use. Typically the ferries that link 2 points by the sea that are quite close, the ferries from, I don't know, from France to England, for example, or the ferries inside a fjord in Norway or Denmark from 2 points of the coast. Let's say you get 30 or 40 minutes of use, and then you get as much time for charging. And again, 30, 40 minutes of use, and then again, as many time for charging on the coast. Okay, it seems to be strange, but it is more and more used and known. Also, so there are ferries in Norway. You know, in Norway they are full of energy. They have both oil, a lot, under the sea level, and also they are full of water centrals. They get mountains and rivers. But also you get Dutch service ships that are going in canals from one port to another port, and it's usually a short distance, so they can have batteries or capacitors as energy source. And what is the most interesting? Batteries for large power. There are coal transport ships in China. Coal, the heavy black material for burning. In China they are using a lot of coal for making electricity. That's why they get a huge smog, like we had it in England 200 years ago. The same situation. People are dying of the pollution of the air. So for larger batteries, you get coal transporting ships in China. So they are transporting the coal from the mine, I don't know, or from one port to another port. So there's a quite limited range of activity for the ship. And the charging time is just equal to the charging or discharging of the coal. So the ship arrives to the port, it's plugged in the circuit, it's discharged, and by the time it's discharged from the coal, it is charging its batteries, and then gets back for the second quantity of coal. Charging time is the same as cargo charging time. So don't be surprised to see more and more ships using electric power. Not the deep sea ships, but ships in river or in lakes. For example, at the Lake Balaton, it's forbidden to have internal combustion engine motorized boat for particulars. See, if you want to have motorized boat from going anywhere in the sea or in the Balaton Lake, you've got to have an electric motor inside. And there are more and more manufacturers for electric boats around the Lake Balaton. It's surprising, but still. It's surprising. Okay. Any question concerning this? So capacitors alone are not used too often, mostly coupled with batteries. But I have heard about buses, for example, and it was planned to have a charging station by bus station. And by the time the passengers get off and on, it charges from 0 to full the capacitor inside the bus. Advantage, capacitor is cheaper than battery and also has less weight. Disadvantage, it cannot store so many power than a battery. So I will finish with the capacitors, and I switch to the next type of energy storage type. So we had batteries, we had capacitors, another third type of energy storage for electric vehicle. But before I erase the board, somehow. And now some words about what we call the fuel cell. Have you heard about? Not yet in high school? No, it was not. Fuel cell is nothing else than a specific device using chemistry again, using chemical energy. Maybe you have heard in chemistry, you have learned in chemistry about the water. That the water, let's have 2 molecules of water, and you can decompose it by electricity. How you can decompose it? You will have 2 hydrogen molecules plus 1 oxygen molecule. You have seen this for sure. And also you have seen the opposite. And the opposite is like 2 molecules of hydrogen plus 1 molecule of oxygen. It gives us 2 molecules of water. And the first is the decomposition. By electricity usually. You get a positive and negative electrode in the water. You put, you switch a kind of tension on the electrodes, and it starts boiling around in the water, and the gas is forming. And when you get hydrogen, and you are burning the hydrogen in presence of air, oxygen, the result will be water mist or water steam that will cool down to normal liquid water. So the fuel cell, what it is doing? The fuel cell is, let's say, burning hydrogen at slow speed. Okay, so it makes the second reaction. That's why I made the commas burning at slow speed. And what is obtained by this reaction? We get heat, we get water as a result of the reaction, heat, water, and electricity. We get back a bit of electricity. And that's what we want. That's what we want. So the composition of a fuel cell is such that you get 2 volumes, two compartments separated by a special membrane and the composition of this membrane is very important. It will have specific layers and specific pores to let the oxygen and the hydrogen enter in contact, but it doesn't allow to have flames and a quick reaction. Okay, is it clear? And it contains expensive, rare metals. You have heard about that a catalyzer in an internal combustion engine, it contains rare and precious metals like platina and palladium and I don't know what. And often people are just stealing the catalyzer from below the car to sell it as scrap to get a bit of money because it's expensive. No. In a fuel cell, you need parts that are, let's say, 100 times more expensive. So it's really expensive. Much more expensive than a battery these days. The technology was elaborated for the space industry. If you have heard about the Apollo spaceships 50 years ago, with that came to the moon. Now this was the first presentation of this technology. And since then, it still exists, and it became cheaper, cheaper, and cheaper, but even today, it's quite expensive. Okay? So how it works if we want to use in our car? In actual state of development. Heating is required for starting. It's like the 1 minute heating up of an old diesel, the same range. Let's say 1 minute approximately. And after it has heated up, it works more or less. And also regulation of power is slow. Again, I can say like an old large diesel engine, it works at a given RPM, and if you want to change it either down or up a bit, it takes time to get a new RPM. Okay? And for these reasons, usually we couple the fuel cell to a quite large battery pack. So this battery pack is first heating up the fuel cell while you are starting the car in the first minutes. And also it helps to, it's a kind of tampon battery. If you need quickly a lot of energy, then this is the energy of the battery that is consumed. And by the time the fuel cell heats up or gives more power, it will recharge the battery after. Okay, this is the case. And then. So not only the fuel cell is expensive, but also it requires a quite large battery pack with it. When I say large battery pack, it's like in the Prius, the Toyota Prius. So let's say in the compartment of what's below your rear seat in the car. Not for a complete chassis like in a modern electric car, smaller one. Let's say the surface of your rear seats in the car. That's what is required. Okay? So, what is the advantage of the fuel cell, though it's very, very expensive? Advantages. Advantages and disadvantages. The most important advantage that it uses hydrogen. Why is it so important to use hydrogen? That's because hydrogen can be also used by the classic internal combustion engines. So if you get a network in which you can buy hydrogen, you can use both the classic engines and electric engines. So you get a common network for the two. For a battery electric vehicle, you need a separate electric charging point, different of the internal combustion engine's usual petrol stations. With hydrogen, you need just one network for energy supply. Okay? Internal combustion engine cars. And from where we get the hydrogen? The problem is with the gas and gasoline and diesel engine is that it comes out from the soil, from a source that has been produced in long millions of years. And once we have no more, then we've got to change our energy source. While hydrogen it can be produced just from water. And once it's combusted, again we re-get the same amount of water. So we are not consuming, we are not producing carbon dioxide while using hydrogen. Okay, so it is CO2 neutral. And more, hydrogen can be produced by the so-called green energy. What does it mean? It means that you got solar plants or wind plants around the seaside, and the energy coming from the solar plant or the wind plant can be used directly for decomposing water and creating hydrogen. And you use the hydrogen for your traffic purposes, and what goes out of the exhaust of the fuel cell vehicle, you get pure water. So no carbon dioxide production, which is quite important for the climate variation, climate change that we get now. And also one important thing is that quick refueling, the time for charging a fuel cell vehicle is really quick, in the same order than charging a normal gasoline engine. You got the plug at the station, you control the ceiling, it starts to charge, and in 1 or 2 minutes you are ready. For a battery vehicle, standard charging time, maybe I was talking about, it's like 30 to 40 minutes, up to 80% of state of charge. So it's 10 times more, at least 10. I say 3 minutes for hydrogen, 30 minutes for battery electricity, it's 10 times more. So hydrogen has got a lot of advantages. You can transform your petrol stations to hydrogen station. You get the natural gas stations. It requires similar service apparatus. But, and there's a but always, it's not so rose that it looks like. If you remember what had happened to Hindenburg, the spaceship or the airship Hindenburg. A big fire. Yeah. So hydrogen is not only carbon neutral and not only easy to produce, but also it's highly flammable, like lithium also. It can catch fire really easy, and the flame has no colors. So unless you touch it, you don't see it. And because it's so small, so 1 proton and 1 electron for an atom, and 2 protons and 2 electrons for the molecule, it's quite difficult to handle, to store. So the negatives is the storage of hydrogen. It's not obvious at all. It has very little energy content. So either you need a huge volume of hydrogen gas, or you've got to compress it to high pressure to store enough energy for a given 400, 500 kilometer distance, which is the usual range of a car with gasoline. So the storage, either high pressure or high volume, or as hydrogen molecule is really small, there are materials, solid materials, inside it goes under certain pressure. So like you have a sponge for hydrogen. And in certain materials, you can push in a lot of hydrogen. But again, it requires pressure, or diluted or hidden in sponges. Under pressure. So just imagine in your car you get the cooling water at, let's say, 1 bar of pressure constantly, 1.5. You get a turbo on your engine, it goes up to 1.5 bars or 2 or 3 bars in racing cars. You get a braking circuits in the hydraulics, you get 100 to 150 bars. In airplanes, you get circuits up to 400 bars. But it requires specific materials and quite careful handling. And then you get your fuel cell car, inside which you get the hydrogen at 700 bars. 700. And worse, it's in balls, in storage devices that are made of plastic, reinforced, fiber reinforced plastic, not to be too heavy. And remember, if you get a car that goes with normal, regular gas, liquefied petrol gas, for example, you get steel, no, how to say it in English? Steel reservoirs that you've got to check every 5 years and change every 10 years. And they are made of steel, that is a material that we know quite well from the point of view of fatigue and work under loading time. But liquefied petrol gas, it goes up to 6-7 bars in this range, less than 10 bar, I suppose. And you get something that is 10 times higher at pressure, 770, 700, 100 times higher in pressure, plus you get the compartment in plastic. For sure, you've got to change it after 10 years. For sure. And even if there's a leak, it's quite difficult to handle. Have you heard about large ships that are transporting liquefied gas, natural gas? You get a large white ship with 1, 2, 3 large reservoir in white, spherical reservoir painted white. Why exactly white and not red? For the heat absorbing, yeah, for minimizing the heat absorbing capacity. And even like that, the pressure is continuously increasing during the day and decreasing a bit during night. So large ships like that are using gas engines, not diesel engines, but gas engines, because if the pressure reaches a given limit in the spherical reservoir, either they release the pressure in the air, that's all, or they use this released gas for driving the ship. Okay, so imagine you get, let's say, 20 cars like that in a parking lot on the sun. Red cars, black cars, yellow cars on the sun. Okay, do you see? How to handle the pressure increase in a reservoir like that? Will they release the hydrogen in the parking lot around? If somebody goes there smoking, just putting away the cigarette. Okay. So it's not really obvious how to handle these things. For sure, these things will be solved somehow, maybe by switching on time by time the fuel cell for consuming the overpressure, so it can happen. But still, there are some questions to ask. These days, we don't know which way will be the best. Batteries, capacitors, fuel cells, or a combination of these. In 20 years, we will see it. By the time you get enough experience in your engineering life, you will see it. I'm curious to see the first fuel cell-driven tank and fuel cell-driven airplane. I have heard about fuel cell-driven buses, because in bus you get a lot of place for the larger fuel cells and larger hydrogen tanks. Passenger cars, you can buy it. As passenger car, you get the Toyota Mirai, the first commercially or second commercially available fuel cell vehicle. You can buy it in Japan, or not buy it, just license it or lease it for a given time. Then you've got to give it back to further analysis. And also these were the Koreans that made the first commercially available fuel cell car. It was, I don't know what was the name, but it was Hyundai in Korean. So they had it just by request, by consumer request, but they produced some of these fuel cell vehicles. The Toyota Mirai is a normal free to buy car in Japan. I have seen some of this in Budapest also. It's rare because there are no hydrogen stations. Okay, and the second thing, price of fuel cell. It's really expensive. And obviously, where are the mines for expensive materials like palladium and platinum and so on? Either in Africa or in China. So it's not the safest source, actually. Okay. Now, I think we have 10 minutes left. I will finish it now. And next week we start with the electric motors. Okay? I don't want to start it because it's just the beginning. Okay? Was it clear? Yes? Have you heard about it in high school or other studies? Electric motors, yes? AC, DC. In details or? Not in details. Oh, I will try to make a bit more. Not so much still, but you will see. And about fuel cells and batteries, have you learned anything?
Yeah, hydrogen one is we heard about it.
Sorry?
The fuel cell.
Fuel cell? You have heard about it. Okay. So thank you for your attention. We will finish it for today, and we will continue next week. And you get the second test. The second test you get at 17 hours, so 5 hours in the afternoon, on the usual Moodle system. So you've got to log in, and you can fill in the test from 5 hours in the afternoon till 5:20. Again, 10 questions. Okay. Good. Any other question? No? Then thank you for coming, and see you on next week.